Welcome to another episode of We Are Carbon. I'm Helen Fisher and I'm joined by David Nicholson of Natural Building Systems for a discussion that continues our ongoing exploration of the idea that what's healthy for the planet is also very much healthy for ourselves. But this time we're moving the focus to construction. If you've ever peeped into the rabbit hole of the impacts of our built environment upon the climate, the natural world or our own bodies, you may have felt that desire to step back into ignorance. Highly dependent on extraction, huge outputs of toxicity, and all to create homes that can be a breeding ground for black mould. It is hard work to be a regenerative consumer in today's world. And this is all the more true when we switch our attention from the food that we buy to our homes. But as we see so much wonderful development going on in the world, paving the way to a much more regenerative future, companies like Natural Building Systems are bringing our homes along with that. As David talks us through why it's so essential that we bring a paradigm shift to our approach to building, I love how the solution he's been developing ties things right back to the soil. He has a fantastic range of experience and insights to offer, and I feel it's a discussion that really highlights the need to see our developments as a full picture, connecting and supporting across industries and specialisms. So whether you are a farmer, work in construction, or simply live inside a home, there should be something of interest here. I hope you enjoy.
Yeah, so I've been involved in construction for over 30 years, and in one way or another, you're fixing up old buildings mostly, and then some new builds. And I guess I just became increasingly aware of the many construction related problems, and the built environment in general, carbon impacts in particular, the waste, the inefficiency. But also the fact that we're kind of forced to live in unhealthy buildings. We live and work in places which are generally kind of vapor closed and surrounded by plastic. I mean, it's really actually quite shocking just on that alone. I mean, we're literally surrounded when you consider that pretty much everything has plastic in it or on it. Flooring, furniture, the paint on our walls. I mean, you just can't escape unless you make a really big effort. And I guess also the challenge of making buildings with such a limited range of options was kind of frustrating and depressing in equal measure. So trying to find better materials. And you honestly need to be a bit of a sleuth to find out actually what's in things. It really, there's so much greenwash, obviously, and not at all helped by the eco prefix, which, products which might save you a few quid on your energy bills, but, may also release VOCs or gradually poison you by other means, and often with upfront carbon that will never be repaid in the operational carbon saving. So about 4 years ago, I co-founded Natural Building Systems with a friend who, coming from a farming background, had been trying to persuade her family to grow industrial hemp for good farming reasons, but also because hemp has been used for many decades as insulation in buildings. And I'm sure we'll come on to the very many remarkable attributes of hemp as a construction material. But the upshot was we decided to set up, it's kind of a mission really, to develop a construction system using entirely natural materials, which you could think is there are straw solutions and other hemp solutions, but they're not very systemized. And systems thinking is really kind of behind everything that we do. It's really just looking very closely at system boundaries, which is highly relevant for carbon accounting. And how do you make these high-performing materials more affordable through a systemized approach to their production and use?
That's fantastic. And I think you've highlighted there just how big a scope this built environment is. You've mentioned about the unhealthy environment that we create with the VOCs. And I think that is a topic that people easily overlook when it comes to our health, and the sort of side-by-side impact, the sort of unhealthy human environment and the output of carbon that comes in the toxic sort of pollution.
Yeah, and they're very closely linked. They're very closely linked. You have to look at both. You can't just look at one thing in isolation.
Absolutely. And I think that today what would be fantastic is to try to hone in on a focus, and you've touched on it already, this idea that a building has this embodied carbon that can never be reversed once it's kind of gone into the construction and the carbon's gone into the environment. No amount of insulation or green tech is going to sort of take away that impact that it's had on its sort of embodied carbon.
Exactly.
So you have this concept in mind, which I think is beautiful and very poignant to sort of describe, to turn a building into a carbon sink. So if we put the focus on that today, we are turning that issue in reverse and saying, well, actually, this building has brought carbon down and is holding it there. So if we focus there, I think what we need to do is get a little bit of context, and maybe you could give us a sense of the current situation. How significant is that embodied carbon, and how well is it being addressed?
So I think in order to look at the current situation, you've got to look back a little bit as well, because, I mean, it's not a new idea to make buildings as carbon sinks. And inadvertently, humans have been making buildings as carbon sinks for most of human history. It really, right up until the Industrial Revolution, that was normal to build. I mean, where I live in East Anglia, it used to be, until about 200 years ago, that you'd build houses with an oak frame, which was often made off-site. You'd use the local materials of clay, so wattle and daub. You'd use thatch, straw thatch on the roof, and you would create a carbon sink. So the amount of carbon sequestered in all those materials would far exceed the carbon emitted during the production. I mean, frankly, most of the production was just kind of from the sweat of the brows of the people making that building. So, and this was the case for thousands of years. It was normal. It was only really since the advent of cheap fossil fuel energy that the availability of building materials, which had much more high energy content, so masonry bricks and steel, and that tipped the balance towards buildings that embody significant amounts of carbon, far in excess of the carbon locked away in the materials. And so it's really important to kind of recognize that where we're at now is anomalous to where we've been in the past, and it might feel like it's normal to make buildings as we do at the moment, but it really isn't when you look at the human history and the built environment in general. And of course, now houses in particular use materials shipped from all over the world using incredibly high energy production processes. So that means that a typical two-bedroom masonry house emits about 35 tons of carbon net. So net as in, if you deduct the biogenic carbon sequestered in the timber elements, etc., and net that against the overall carbon, embodied carbon, you get to about 35 tons, and it's it's far too much. It's not necessary. You can make buildings which sequester more carbon from the atmosphere than it takes to make them. And the cumulative effect of all these high embodied carbon buildings is that the carbon embodied in construction materials and products globally amounts to about 11% of global emissions. 11%, it's not as much as the global emissions associated with the use of buildings, and that relates very much to energy efficiency. But it is significant. I mean, if you compare it to aviation shipping, you get to about 5%. And these are kind of very visible symbols of kind of excessive carbon consumption. You think, okay, that aeroplane over there, obviously it's having a big impact, but construction materials far greater, and it's all kind of invisible because no one really goes to look at all the, Portland cement factories, etc., and the steel factories. This is all just being pumped into the atmosphere. I mean, concrete alone is about 8% of global warming gases. So it's the case now that even before you step through the front door of your new house, if it's built of masonry, then more carbon's already been emitted into the atmosphere than will ever be emitted during its service life, especially when you take account of the grid decarbonisation, just the existing energy efficiency measures. That's completely transformed the calculus over the last 10 or 15 years. It used to be absolutely the case that net zero meant that you've got to be addressing operational carbon use, and of course that's really important. But it's kind of that's a problem that's been solved. It's not difficult to produce a net zero building operationally. You just add enough insulation to keep it warm. But actually, that kind of rather crude approach can sometimes mean that you're putting more carbon into the atmosphere than you, over the whole life cycle of the building than you would be if you're looking at the upfront carbon in more detail.
Yeah, there's some really significant figures there, and just to sort of summarise for people, the 2-bedroom home that you've had built out of masonry, this new house, has put 35 tonnes of carbon into the atmosphere for being produced.
Well, that's a net figure. I mean, so, if you look on the internet, you'll find other figures, more like 50 tonnes. But we use net figures because perhaps controversially, we absolutely do look at the biogenic carbon captured in the materials. And there's a lot of debate around LCA methodologies, whether you should or shouldn't account for biogenic carbon. We do, and we do because of the real world consequences of design decisions. But obviously, if you can remove carbon from the atmosphere in the short term, especially using short cycle carbon capture materials, not just timber, and if you can do that, then you're of course, if you can also deliver operational carbon savings, but those savings are over many decades into the future. And the problem is right now, we've got to make really radical changes over the next 10 or so years to transition to a completely different economic paradigm. And it's not just on the question of climate change, it's on the question of things like peak cheap oil. That's going to have an increasingly a big effect on the way we live our lives. And this is why we come back to a kind of systems approach, because you've really got to be looking at all these dynamic systems which are interacting with each other. You can't just look at carbon on its own. I mean, carbon's kind of underneath everything else, but it's really important to be understanding that there's an economic paradigm which we exist in now, which will change, and we obviously want to try and promote a change which is better for humans and better for the planet. And I think one thing which, I mean, so many kind of climate change related issues are seen as a okay, I won't be able to go on holiday anymore, and I'll have to sell the car and just eat vegetables. Actually, what we're saying is you can actually have a better performing house. You can have a more healthy environment. It'll last longer. You'll have better air quality. You won't have black mold growing in the corner, because natural materials are actually higher performing than the synthetic alternatives. And it's kind of being forgotten because we just accept that all these kind of manufactured products, which we're kind of forced to use, are the best technology available. Actually, it's the case that natural materials really can perform much better than the synthetic alternatives, and by which I mean not just addressing U values and air tightness, looking very much more widely at what is a healthy indoor environment, and thinking about how do you avoid summer overheating, and how do you stay warm in the winter without having to turn the heating on. You've got to be thinking very much about the diurnal cycle. You've got to be looking at how long it takes for heat and cold to get through the thermal envelope. That's quite distinct and different from U values. And there's so many kind of metrics which effectively are oversimplified, which essentially benefit only very narrow interests, commercial interests, essentially. And if you think about the global insulation market, 98% of that is synthetic plastic foam insulations and mineral wools. 2% are natural insulation materials.
I think that's a really fantastic point to highlight, because it encompasses this idea that you've brought to us, which is that the net zero targets of looking at operational costs alone are actually embodying or emitting more carbon into the atmosphere because of this high percentage of synthetics.
Well, it absolutely can do, and there's been some really interesting studies. Actually, there's one in Canada which looked at the inflection point. I mean, Canada's got a high level of grid decarbonisation. They've got a lot of renewables, so you have to look at each different region separately. But what was interesting about that study was that looking at especially plastic foam insulations, even before you get to sort of what would be the kind of equivalent Part L, so like, what the minimum building code is for insulation, because you've got kind of diminishing returns in respect of the energy efficiency delivered by additional layers of insulation. So you can double the amount of insulation, and you won't double the energy efficiency by any means. There's a very much a kind of curved graph which shows a sort of diminishing return for the effect of the insulation. But of course, the addition of insulation in itself has a carbon impact, and that's entirely linear. So you double the amount of insulation, you double the amount of embodied carbon that you just put into your insulation build-up. And that inflection point is so important, because we get so many people coming to us and saying, okay, well, I want a passive house, and passive house can be exactly the right answer, but it's not the answer to everything, because and especially if you're delivering that level of thermal performance using synthetic insulation materials, which have in themselves relatively high embodied carbon, that if you're looking at whole life cycle carbon, you're actually just increasing the carbon footprint of your house. And there is a reasonably kind of simple way of assessing that balance of. You have to do the calculations. You've got to look at actually what are the upfront embodied carbon, and also look at GWP, global warming potential of the materials themselves. I mean, so many of these foam plastic insulations, I mean, they're pumped full of gases, which in themselves have global warming potential. I mean, they've only just got over using HFCs, which had hundreds of times the global warming potential of carbon dioxide. So they, and these materials are totally unrecyclable. Once they've been used in a building, and if that building is ever demolished, they can't be used for anything. They just end up in landfill, and they emit all these gases. So it is so often the case that if you're just looking at solving energy efficiency, you're actually quite often increasing the carbon impacts of a building.
Yeah, that's incredibly poignant, I think, for people to sort of acknowledge. And in a very sort of simplistic way, when we look at the embodied carbon in a building, we can attribute that in a huge way to these materials such as concrete, cement, masonry, and then these synthetic insulations. So if we to turn that into a carbon sink building, a building that is embodying carbon in a sort of, it's holding it, it's sinking that carbon, then we would presumably switch to natural materials in as many of these areas as we possibly can. Do you have any thoughts about the benefits or the differences between utilising materials that have a long life cycle like timber versus sort of agricultural crop residues, hemp and straw, so they're sort of more short life cycle plants?
Yeah, but you say the short life cycle. Okay, so they're short cycle crops in as much as they grow over a year, but they're not short life cycle in their durability or longevity. And that's a really important thing to understand, because like any cellulose or cellulose-based material, you can maintain. They will last forever if you keep them below 20% moisture content. It's only when they have too much moisture that they start to degrade. And but the relationship with moisture is really a key concept, because we use hemp, and we use hemp because it has these very particular moisture buffering characteristics. It's highly hygroscopic, and the hygroscopicity is the thing that actually moderates indoor relative humidity. It reduces the peaks and troughs of the diurnal cycle, and it has this. So it has a thermal mass greater than its physical mass. So essentially, although a lightweight material, it's performing as if it's much more dense. And that moisture buffering capacity actually is the thing which also gives it better durability. So if you have a cavity wall with mineral wool insulation in it, and the mineral wool gets wet, it doesn't dry out because it has very poor capillarity, and capillarity is the thing that allows materials to dry out effectively. On the other hand, if you're using natural materials, wood fibre, hemp, etc., that's what they do. They just, they're constantly absorbing and desorbing moisture, and that in that process, it has this thermal buffering effect as well. So I don't know if that's a bit of a diversion from what you asked, but it's a really key concept, because using biogenic materials is not a compromise. It's actually giving you a much higher performing building, which does a lot more than just simply, keeping the heat that you've maybe created through some bit of technology, a heating system, whatever. It's doing more than just keep the heat in. It's allowing this kind of constant dynamic process between the temperature outside and the temperature inside, the humidity inside, the humidity outside, and it is essentially making the materials of the building do a lot of the work of maintaining comfortable indoor temperatures and humidity.
Oh, I think it's incredible, and the way that you describe the hemp, it's almost as though nature has provided the perfect engineering solution with regards to the way that this is it's just got these properties that I bet that would be very challenging to recreate in a lab of all the scientific expertise to create a material that has such fantastic thermal properties.
Well, and exactly, and nature-based solutions in other parts of our lives are kind of just taken for granted. You know, if you have a woolen jumper, you don't think, oh, it's never going to be as good as a nylon jumper or whatever. You think, okay, wool just does good stuff, and you can see that obviously there's constraints, etc. But it's a given that natural materials perform better for certain things. And it's the same in the built environment. You don't have to set up a petrochemical derived process to make a high-performing insulation material, because actually, what are you doing there? You know, you're actually just encouraging oil production, and it's about, you know, the petrochemical-based insulations are just a sort of derived from a byproduct of the global petrochemical industry. And of course you can get really slim build-ups with PIR insulation, but it's just in a way it's shocking these materials are even allowed, because they are highly toxic if they burn. You know, they release hydrogen cyanide if they burn, and so it's kind of solving a very limited scope problem of essentially, you know, developers want slim wall build-ups because they don't want to lose internal space. And okay, so you can get the same U value with a slightly thicker wall build-up. They've lost a few millimeters of space, but it's doing so much more. You know, it's actually moderating moisture in the indoor environment, and that relates to so many problems now. You know, and it's kind of interesting. And you know, forgive me if I'm rambling on a little bit about the question of systems, because what I was really conscious of last winter during the energy crisis was the kind of the overlap of the socioeconomic and political systems in different regions. So, okay, Vladimir Putin decides to invade Ukraine, and you get black mold appearing in people's corners of their room. How is that connected? Well, it's connected by the simple fact that everyone turned their heating down. You know, they couldn't afford the energy anymore. And we live in a country with very poorly insulated houses. You turn the heating down in your poorly insulated house, you're immediately going to have condensation problems because the dew point changes. And that is what creates the black mold. And it's really important to be looking at all these different dynamic systems. Obviously, we're not going to be able to do anything about Vladimir Putin, but we can do something about our homes. We can actually look at how we insulate them.
That's actually a really incredible kind of visual that you've kind of connected there. I think it really highlights the connection of everything very wonderfully. And to go back to this sort of idea of the short growing materials, I think that you've really kind of highlighted the idea that these are just as durable as timber, and they're fantastic in terms of the properties that they have. The reason that I wanted to sort of bring up this comparison was more so because I think the reason perhaps that we use so many petrochemicals, so many synthetic insulations, is just the sheer scale of the construction industry, and how do we ensure that we've got enough materials to build these properties. And when we think about the answer being timber, there's a big concern there of deforestation and the time that it takes to replace these.
And that, as they absolutely should be, yeah, because it's, you know, it's very resource intensive. But we often look at comparisons with, I mean, in our construction system, we very much try and focus the functionality of our system against material efficiency. And what that means is Of course, you can sequester huge amounts of biogenic carbon if you're using mass timber solutions like cross-laminated timber. So typically you have like a 4-inch panel, and you've sequestered a lot of carbon in that material, but it's not material efficient because you don't actually need, from a structural perspective, that much material to hold your building up. And what we are really interested in is how do you optimize materials for their specific functionality, so that you have, so hemp, for example, is typically used in 400 or more deep monolithic build-ups, and it uses a lot of hemp, which is in one sense fine, but what we're interested in is you actually only really getting the hygrothermal benefits from the first 100 millimeters of it. So we only use 100 millimeters of our hemp composite on the warm side of our wall build-up, and we use other materials to, like hemp fibre, wood fibre, etc., to deliver the necessarily sort of compact wall build-up. And the point about short cycle carbon capture crops is that many have great characteristics from a performance point of view. So things like straw and other materials, which clearly also sequester a lot of carbon. They don't have the same hygrothermal characteristics, which is key. But the interesting thing about hemp is it is actually pretty much the most efficient way of sequestering carbon from the atmosphere, second only to bamboo. It grows incredibly quickly. It grows pretty much in any region of the world. And it's about 14 tons, thereabouts, carbon equivalent per hectare per year. You compare that to forestry. Forestry, get an average about 4 tons carbon equivalent per hectare per year. So it's far more efficient, and also you're not waiting decades for it to mature. And it's grown as a break crop, so it means that it's not actually competing with food supplies. And we spend a lot of time talking to farmers, actually, and farmers are desperate for alternative break crops because they have real problems with various pest issues, and flea beetle in particular is a real problem for the farmers we're talking to. And they want to see, they want alternative break crops to break those pest cycles. And the wonderful thing about hemp when you grow it is that it actually improves the soil quality. It breaks through the soil horizons. It's got very deep tap roots, and that process of improving the soil actually increases subsequent food crop yields. So not only is it not competing with food supplies, it's actually improving food supply. So it's very different from timber, which obviously does compete with food supplies. If you grow 30 hectares of forestry, that land is out of food production for the foreseeable decades, I think it kind of shifts the debate about how you account for the carbon, which is why we come back to this question of, so in carbon accounting methodologies, typically you would have a kind of -1 +1 approach. So you'd count, you'd take out the carbon sequestered at the first stages of your calculation, but you'd also add it back in. And the assumption that at the end of the notional surface life of the building that you have to assume that it's going to go into landfill or into energy use, and therefore it's essentially neutral. And our proposition is actually, if you're using short cycle carbon capture crops as your primary construction material, then it's reasonable to take a more dynamic approach, that you're looking at the early stage upfront carbon impacts, and you're looking at what's the net effect of the biogenic carbon removed from the atmosphere.
Yeah, it's a fantastic solution to look to these crops, and it excites me in that we can have this discussion that we're talking about the built environment, but it also connects back to the soil. which is such a huge focus of what we talk about on the podcast. And the idea that we can sequester carbon into the soil, that we can improve and rebuild soils. And there's a crop that hemp comes up so much in regenerative discussions as a solution in so many different ways. Have you mentioned at the beginning that you sort of started on this journey with a friend that is a farmer, and she's sort of looking at the hemp crops. Have you been able to build that relationship directly with farmers and continue?
Yeah, totally. So we're doing a lot of work with farmers, and we're actually at the moment on a UKRI funded program with 24 other partners who are mostly farmers, led by the National Institute of Agricultural and Botanical Research, where it's specifically about looking at different crop systems and seed varieties, etc., for optimizing the use of short-cycle carbon capture crops for use in construction. So there's some of the partners like us are looking at the kind of as essentially as customers of the crop production, and it's often the way that actually farmers they want to grow these crops, but they also want to know that there's customers who'll buy it. Hemp is actually it's not the easiest crop to grow, not least because of the regulatory framework, but also because it requires quite specific types of processing and production. And that's something actually interestingly we're addressing by looking at how you can avoid the very significant upfront investment in decorticating machines, etc., and use more commonly available forage harvesters, etc., to make what is in effect a rather kind of low-grade material, but that is absolutely fine with us for our particular biocomposite which we've developed. So the work we do with farmers is really key. Actually, we're working with a farmer locally who would want to grow hemp and is also interested in providing us with a factory premises on his land for the specific reason that it needs to be close to the source of the production, and it really is an opportunity to decarbonize both construction and agriculture at the same time, and so many of these things actually, if you're willing to encompass quite a sort of broad objective, become convergent on a single point, that actually, it's not necessary to ship things in from all over the world. You can grow materials locally to make your buildings, and that what we're exploring is a kind of distributed manufacturing model where you can set up relatively inexpensively near the sources of the feedstock materials and produce high-performing homes. Now, I say that with slight reservation because we're not actually producing homes, we're producing the components for homes. And so what we do is essentially make a kit of parts for construction. And it can be, frankly, any building typology, but it's something where it's particularly suited for dwellings because it tend to be only a couple of stories, and it is where the biggest challenge is in terms of transforming the industry. I think I may have mentioned to you before that about 90% of the homes in our country, in the UK, are still built with conventional cavity masonry walls, and we're obviously targeting that huge potential for transforming those impacts, the carbon impacts, and producing something which doesn't cost anything more and actually performs better than the existing solutions.
Yeah, it's like you've mentioned it a number of times, this sort of systems thinking approach, and it's very, very clear that those benefits they continue to expand, and because of the connections and the potential for growing materials locally, processing locally, and building those components, there's huge logistical savings there and a massive opportunity for farmers and processors alike to sort of get in on this sort of new market potentially. That presumably is becoming slightly easier for farmers to look at growing hemp because, like you said, the regulations on it can be challenging.
Yeah, so it's a mixed message because it's a you have to obtain a license from the government, and it's kind of an unnecessary obstacle. In other places like France, it's much more easy to grow hemp. Industrial hemp looks identical to cannabis, and so our war on drugs involves us making it difficult for farmers to grow it. There's obviously also in this country perverse obstacles such as you can't grow it for the seeds. The seed is the most valuable part of the plant. You can import the seed and you can sell it in shops as a CBD oil or whatever, but you can't grow it. And so there are lots of obstacles still to address in the regulatory framework. Maybe one day that might change. In the meantime, we're just interested primarily in the shiv, which is the kind of waste product from the fibre. And the fibre is used in a huge range of different textile applications, but it is a viable crop, even notwithstanding the lack of you can't grow it for the seed, and there have been sort of quite notorious instances of hemp crops having to be ploughed back where there was a suspicion that they weren't actually being grown just for the fibre or the shiv.
Well, yeah. So that does add a huge complication, but hopefully things will go in the right direction.
It's not insurmountable, and certainly the farming partners that we're talking to are up for the challenge because they can see there's such distinct farming benefits. I didn't mention one of the real advantages of hemp is it doesn't require any inputs, so you don't have to spray it, and that's great for biodiversity, but it's also great for farmers who, frankly, have seen huge price increases in their inputs for other crops, and to have a crop which they can actually use, which is improving the soil quality and disrupting pest cycles, which doesn't require spraying, then that is reason enough to grow it. But we're working very closely with, as I say, various partners to in a way produce a kind of roadmap for farmers so that they can be reassured that it's something that they can do. At the moment, we're getting all our hemp from East Yorkshire, which is the only place in the UK that grows it on a commercial scale. It's far too far. I mean, it's a bulky material, and other places, other regions of the world have much more local production and use, and it can happen here. We just need to get to a place where farmers are more clear of the fact that there's a kind of supply chain ready for their material.
Yeah, wonderful. It sounds like a huge potential opportunity. So fingers crossed it keeps going in the right direction. And if we talk a little bit more about what you're actually creating, because these materials, as you've mentioned, that we've used them in buildings for hundreds of years, and there's a lot of labour, there's a lot of sweat that goes into constructing a house out of maybe straw or hemp or cob. How are you creating what you've described as components that can be sent out for almost kind of flat packing a building?
Yeah. So in a way, there's kind of two strands to our work, and one is all around materials and biobased materials in particular, and the other is in optimizing and the use of digital tools, and there's huge potential there just in itself. I mean, it's really, to some extent, kind of surprising actually, even within the off-site manufactured sector, that digital tools really aren't used to the extent that they could be. And this is not just in the production of construction components. It's also in the way they're designed and how that design integrates with the manufacturer. So our work is really, we're working with some fantastic digital partners actually who are helping us in things like VR solutions, so that you can visualize more easily your the three-dimensional design of your project, with other partners who are developing parametric configurators, which enable you to very quickly configure a building using our components, and very quickly see what the carbon and cost implications are of small changes. The surprising thing about a lot of design actually is it's still done in a very 2D way, and that it is changing. We use we develop a very detailed 3D model, like a digital twin of the building that we will make, and that is very kind of driven by the need to create cost efficiencies. And I mean, we would do that anyway, but the thing about cost efficiencies is that you're using inherently more expensive materials, and they're more expensive because they don't have the massive economies of scale that the other synthetic materials have. And so you're already kind of on the back foot, but you can absolutely address that using a more efficient process, starting right at the kind of design concept stage and developing designs using a kind of integrated approach, by which I mean actually ensuring that you don't have these kind of transactional losses in between each stage. So in construction, there's huge problems around transactional costs because there's so many different layers of involvement with consultants and specialists and designers and engineers, and then you got the contractors and the subcontractors and the specialist contractors, and each one of those layers of involvement is pricing for risk and the transactional cost of delivering their particular aspect of a project. And what we're interested in doing is reducing those transactional costs by having a much more integrated design solution and design, manufacturing, and delivery solution. And it's I guess it's already there in the world to some extent already. So you go to some out-of-town distribution hub, you see lots of portal frame steel buildings, and they're all essentially a kit of parts approach to making buildings very quickly. But they're using incredibly high embodied carbon materials, and they're pretty much agnostic to the question of sustainability. They just do something in a very simple way. What we're interested in doing is providing much more design flexibility so that you can actually design whatever sort of building you want without constraints that there is a design solution for every detail, that you're not having to kind of reinvent the wheel every time you look at a project, that you don't have to say, okay, well, this has got a ring beam, what are we going to put it on, how are we going to support the wall, etc. Okay, so these are problems which come up with it's not even a problem, it's like this, how do you build a building? There are solutions which we can develop and essentially have a library of components which meet every requirement, and that has the combined effect of significantly reducing design lead time, so you can design things more quickly. You can, by improving the design workflows, you're essentially reducing the design costs. Whether that's necessarily reflected in what the client pays or not is another question, but it certainly has the potential in future to make designing buildings much more cost effective. And then because you're integrating the the digital manufacturing tools with the digital design files, there's not this kind of secondary design process, which inevitably also costs money. So really, at every stage, where our focus is how do you make this more efficient? Because we absolutely have to bring the overall cost of the building down to cost parity. Because I mean, typically in the past, using high-performing biogenic materials would attract a premium of around 30%. You know, if you're just using hempcrete, for example, or straw, etc., you might reasonably expect to pay at least 30% more than if you're using so-called conventional materials. And we, I suppose, have a view that the sustainable choice should be the affordable choice, and that it shouldn't be it shouldn't be like a rich niche product that only rich people can afford, that it can actually be something which, if it gets to sufficient scale, should be at cost parity with the alternatives. And to deliver that, every stage has to be more efficient, basically.
Yeah, I think it's a fantastic approach. It sounds like you've given a lot of consideration to ensuring that it becomes a reality that you want to create, not just something that's out of reach. And that's very admirable. In terms of people getting a sense of what this is and how you're offering it, we can put some links in so they can go and see it on the website. But essentially, if we think about something like timber or steel or masonry, there's a very clear sense of this offers structural strength. It offers a lot of strength.
Yeah.
What you're sort of using with these is like a composite board that is creating that strength.
Well, it's a structural cassette, and so that's the core of the system. We have a kind of a range of standardized, repeated components which are effectively breathable structural insulated cassettes. I hesitate to say structural insulated panels because SIPs are very prevalent in the built environment and are typically made with plastic foam type insulations, and actually have all sorts of problems relating to moisture control. And the breathability is absolutely key to everything. There's some really great kind of CNC ply box solutions, but they're not breathable. And yet it's in a way it's a shame, because they have really great characteristics in other ways, but you're kind of missing a trick in a way, because the breathability, it's not. I mean, breathability is all about moisture. It's not about air. It's about how does the thermal envelope manage moisture, and how does it allow moisture through the envelope of the building so that it doesn't become trapped either within the inside space or within the wall itself. And trying to bring these two things together has been really the kind of biggest challenge, because it's kind of easy just to make a kind of CNC box and stack it up and make it structurally work. What's more challenging is how do you also have a good solution for breathability, and that you allow the materials that we're using to perform to their best advantage, really.
Yeah, it sounds like a complex set of work that you've put your focus on, and it's wonderful that people are having this as a sort of new option, because it can be very challenging to take the mindset of creating a healthy building from scratch, and just where do you start with that? So you're offering a solution that people can come to. I think I don't want to sort of take too much of your time and hold you back too long, but if we could fire through some questions about the experience and how it differs from the point of view of the builder and the end user, that would be fantastic. So if somebody is used to building a standard masonry house, how would this differ in any sort of good ways or bad ways?
Well, yeah. So it's a good question, really, because one thing we've been really concerned to do is make the system easy to assemble, so that you don't need specialist skills or like 10 years apprenticeship or anything like that. What you can assemble one of our buildings just with a rubber mallet, but we've developed a connection system with our engineering partners, which essentially is just timber pegs, which you bang in, and it makes it very quick to assemble, but it also makes it straightforward to disassemble and adapt. And the adaptation side of what we do is really key, because it's very rare for a building to stay in its exact same form throughout its service life. It's much more normal that even within relatively short amounts of time that you need to adapt it. You might want to extend it or change the configuration layout. And so it was really important right from the start, when we were looking at the design of our cassettes, to find a solution which enabled rapid assembly but straightforward adaptation. And that means that any single cassette can be individually removed. And it's often a bit of a difficult conversation to have, really, with clients when they oh, I know what I want, and all this adaptation stuff is kind of irrelevant. Well, it may be irrelevant to you right now, but it may be someone in 10 or 15 years' time does want to make a change. Maybe they want to add another story on. So we put a lot of effort into, in a way, scenario planning, thinking about, okay, if this building needs 2 more stories, how would that happen? How would you do that without disrupting the existing components? And a component-based approach actually has a real advantage from a carbon accounting perspective. So we include a material passport in each of our components, and that enables very detailed carbon tracking, but it also allows for the manufacturing files to be attached to each component. It means that you can produce an exact replica of that component and at some point in the future if you want to. But it also means that you can reuse those cassettes in other buildings very simply, because you already know what their performance characteristics are. You know what the structural loading is, etc., and the certifications, etc., which are attached to that component. And it's so important because, without becoming too kind of geeky about it, the LCA methodology is really key to everything, because without a really rigorous circular economy strategy, you really can't claim a carbon negative building. I mean, there's lots of solutions which involve biogenic materials, etc., but really, unless you know how you can adapt and disassemble the building, you can't guarantee that those things aren't going to end up in landfill. And you need incentives, really, to make sure that something which is built to last for many, many decades isn't just thrown away in some future scenario.
There seems a huge aspect of all of this, because when we think about the incredibly short life that a lot of buildings have, and the amount of sort of carbon and resource that goes into them, and in such a short time goes to landfill, I imagine that adaptability is a huge sort of player within the benefits of what you do.
Well, it is, and it's something which has been really lacking in so many other construction approaches, and it's all the more problematic now than it has been in the past. So I mentioned like plastic foam sips, very, very commonly used now to get the U values, but absolutely a disaster so far as any circular economy. I mean, there's just no way you can reuse it. You demolish a building made with those materials, and you just get a pile of kind of stuff which is just unusable, and it's toxic materials essentially. I'm old enough now actually to have witnessed some of these kind of cycles of buildings. I mean, I spent a lot of time in working in Shoreditch, and I can remember the original Broadgate development, and they built it, and then within 25 years, they were completely demolishing and rebuilding the buildings, and that's just a kind of fairly typical office cycle, that they've got their 25-year return on their investment, or probably well before 25 years, and so far as they're concerned, it's like demolish it and start again, or and all those materials are unusable. The steel you can really use the steel, but there's so much in the material which can't be reused because they're not designed for the circular economy. And there is increasing awareness of that as an imperative. The GLA have a circular economy strategy. It's not policy yet, but it is helping to make people think about questions of disassembly.
Yeah, fantastic. And if somebody is to build one of these homes and to live in one of these homes, or it may be used for something other than a home, the experience within that building, I think you've kind of touched on this already. We have less toxicity of the materials. There is breathability, which presumably that kind of issue with black mold is addressed within that. And then what about the costs of running it? The thermal insulation, is that similar to what you might expect in a standard home?
Well, it's better because it's not just looking at sort of static metrics. So a really important aspect of thermal efficiency is relating to what's called decrement delay. So that's the time it takes for the temperature outside to get inside. And that's very noticeable in the summer because if you have a thermal envelope which has poor decrement factor, then it overheats. And essentially, by using materials with very low decrement factor, you can reduce the peaks and troughs of that diurnal cycle. And so it's essentially, if you were to look at an office building with that characteristic, you're reducing your heating and cooling loads, and that relates to energy efficiency. I think the point about having a healthy indoor environment is that it's obviously something that you feel the difference. You don't really see it. I mean, we frequently talk to architects about the fact we don't want our system to be visible. It's an invisible system. It's just in the walls and it's doing stuff. You don't see it doing it, but you can feel the difference. And you really can, actually. The projects that we've delivered so far, in the heat wave we had a couple of years ago, you walk into one of our spaces and it feels like you're in an air-conditioned space because it's so cool. And that's one of the things that hemp does just naturally. Better than an air-conditioned space because it doesn't dry the air. Exactly, it keeps the air at a good level of relative humidity, and like I say, I mean, it's a difficult message to get across really because there's so much focus on kind of the spatial and architectural qualities of the built environment that, and it doesn't really come across in architectural magazines or whatever. The fact actually that you've got a much more healthy indoor environment. And that it's not going to slowly poison you with VOCs and other toxic materials. And I don't want to even go there really because I've been reading a lot about the prevalence of plastics in our environment and the fact that there's like 13,000 different chemicals that are found in different plastics. Obviously, there's a huge range of different plastics, and only about half of those have been tested against the health impacts for humans. Frankly, the other half are being tested on us right now. We're the guinea pigs, and there's a growing body of research to show there's incredibly negative health impacts relating to the chemicals used in plastic. And if that was just one thing that we could deliver, I feel like that would be a big improvement in outcomes because actually there are choices you can avoid. You don't have to have plastic in your paint. You can find breathable paints which don't have plastic, and the same with all the materials we're using in the system itself. it sometimes is a bit of a challenge to find materials which don't have any plastic in. And obviously there's a cost relationship there, which we have to be realistic about. But it's really important to look at not only the kind of moisture control aspects, but just what's coming out of these materials that we surround ourselves with.
Yeah, fantastic. There are so many significant topics that we've covered here. It is incredible work that you're doing, and I really appreciate this opportunity to go through it with you. It would be fantastic if we could leave people with a sense of how can they learn more or get in touch with you. And I think if it's not too presumptuous to consider that both from people interested in construction, but also maybe the agricultural side and the supply chain of hemp.
Well, we're really keen on collaboration generally. I mean, we consider any building project a form of collaboration, and that's kind of one of the main things we're focused on is construction in the past has been rather siloed, and it's almost like a sort of class differential between the people who design it and people who make it, and we're very much trying to bring all that together into one approach, which means that if you want to engage with us on any level, whether it's a farmer interested in growing hemp or someone who just wants to build a house, we're absolutely up for it, because it's really, for us, important to kind of challenge ourselves for every project about how can you make this work, not just from a building health point of view or sustainability point of view, but from an economic point of view, and the commercial imperative to find solutions which aren't too expensive at the same time as producing better outcomes. That's the biggest challenge. It's kind of easy to find solutions which work. The difficult thing is making those solutions cost effective and affordable.
Yeah. Well, thank you so much. We'll make sure that both the website and the contact details are visible in the description. And thank you for being here.
Well, thank you, Helen. I mean, it's been really interesting, and I really applaud your carbon focus. Because it's really absolutely key to everything. And so many of the discussions around sustainability are just far too woolly. They're not really looking at carbon as the thing which actually is underneath everything. And that. It's great to engage with you on the level of kind of the nitty gritty of how do you address this crisis which we're all in, although we might not always know it, around carbon.
And thank you for listening to this episode of We Are Carbon. You can find links in the description to explore more from David and the work of Natural Building Systems. And alongside, there's info to help you learn more with We Are Carbon. Don't forget to subscribe to keep up to date. And let's keep figuring this all out together.